Hello and welcome to this module 29 on manufacturing systems technology. So in the last module we were trying to do some feature recognition and developed an kind of a semi algorithm where the computer can be able to sort of mix and match, and the requirement there was that how you basically create a feature database. So to achieve the feature recognition, obviously what one needs is basically to define the feature precisely, what shape we think is a feature, and then make a database out of it, and we can define any shape as a feature only to those that have manufacturing meanings, and the manufacturing meanings ones are the ones which you think are possible in a particular part geometry to be manufactured, possible for manufacture. So there are 6 commonly used features of that kind where the creation of a database is needed. So these features include a step, a slot, a 3-sided pocket, 4-sided pocket, a pocket or a blind hole, and a through hole. These are all about the kind of features that are sort of corresponding to a certain part. So I have been trying to illustrate this here in these figures right here. For example, there are 2 surfaces F1 and F2, and this can be a, you can call this a step. So this is number 1. This, for example, is a slot, and you have 3 faces here, F1, F2, and maybe another one here, F3. So similarly you call this so this, for example, is a 3-sided a 2-sided pocket. Similarly you have a 3-sided pocket. So the faces which are involved in this 2-sided pocket are F1, F2, and F3, right. This F2 is this particular face. Similarly you have a 3-sided pocket which comprises of 4 faces. So F1, F2, probably another face F3 here, and a face here F4. You can have a blind hole as illustrated here, where you have again 5 faces. So this is F1, there is a face F2, there is actually a face F3, F4, and then there is F5 somewhere here. And then similarly you have a blind hole, so you have a through hole, where you don't have a surface on the bottom, and this can be called a through hole with faces F1, F2, F3, and F4, and there is nothing at the bottom here because the bottom is all machined up. So these are the different manufacturing friendly or possible situations in manufacturing which can be recorded as a part database or a feature database, and then whatever on the drawing you are going to compare has to be in consonance with the parts that are here or that have been represented here. So let us now do an adjacency graph model for these parts and try to understand how the part geometry goes. So obviously you have 2 nodes here corresponding to the face F1, so let us call it F1 and F2, and there is one interconnect between the 2 phases which is of a concave type, and remember that the attribute which was being added to the concavity in the earlier expression was t equal to 0. So this is the graph model for this solid. So you can call this the graph model for the solid which represents the step. Now it is a part of the database, you have stored it somewhere. Similarly in this particular case you're finding there are 3 different surfaces which are there, F1, F2, and F3, and if I record the relationships between these 3 surfaces between F1 and F2, you have an attribute 0, and similarly between F2 and F3 you have another attribute 0 which records the different concavity classifications on the particular part. You also have the 2-sided pocket here as a combination of F1, F2, and F3, where you have a and let's just resolve it in a little appropriate manner so that it appears to be a feasible graph model. So you have F1 and let's say you have F2 and let's put F3 in a triangular manner. So obviously F1 and F2 are connected, so are F1, F2 and F3, and then also F3 and F1 in some way, and all these three are concavities. So this can be a recorded graph model for the two-sided pocket. Similarly, for a three-sided pocket, again you have a set of four surfaces which are interacting with respect to each other. So let's just record these surfaces as F1, F2, and then you can have probably F3 and F4. So F1 and F2 are obviously connected, and so are F1 and F4, and so are F4 and F3 and F3 and F2. And what is also interconnected here is F2 and F3, okay, and F2 and F4, and similarly F1 and F4, okay. So that's how you interconnect the in the case of a three-sided pocket. And further, I would just like to mention here that all these relationships of interconnection are zero. For example, in this case the F1 and F2 has a concavity along this surface. Similarly, F1 and F4 has only a concavity along this surface, so on and so forth. So that is actually representing the graph model for the three-sided pocket. You have a same case with the five sides or five surface models for representing a blind hole. So I am going to actually represent the surfaces here in a little different manner. So you have, let's say, one surface F5 being connected to the other surfaces, let's say F1, F2, F3 and F4, and these are interconnected to each other through concavities and similarly connected to the F5. So F3 is, for example, connected to F5, so is 4, 5 and F2, and all these attributes again are zeros based on the concavity convexity relationship. So F1 F5 or F4 F5 or F3 F5 or F2 F5 are all zeros, and simultaneously also are the F1 F2 F1 F4 and F3 F2 and F3 F4, so on and so forth. So this is the graph model for the blind hole. Mind you, we are recording such models in our overall modeling, because if any solid model comes into picture, now we want to split up that whole surface into a variety of arcs and nodes in the same manner as the algorithm goes, and try to compare with this recognition database that you have created therein. So there is another model here which represents, for example, if supposing there are four nodes that you can see, it is being represented as, you can call it, let me just use the space here, right here. So you have a model here where you have four different faces. Let's say F1 is this face, you have the F2 face, then you have a F3 and a F4, and all the connectivities here are zero, and there is no interconnection between F1 or F3 or F2 and F4 whatsoever. So this is the graph model for a through hole. So once you have defined these features, then the question is, how can you resolve a surface into the graph model and identify in that graph those zones which corresponds to one of these features, and that would in a way allow the computer to logically read what is a feature or what is a non-feature on a certain solid model. So let's look at a problem example now where we talk about, let's say this is the surface which is actually in question, where we can split up into the different parts, different surfaces, and the graph can be potentially drawn. So in this recognition algorithm, what is needed is that you develop an AAG model of this object, and from the matrix representation of the AAG you have to recognize that this right here is a slot, for example, which otherwise for a human being is very easy to be realized, or this here, for example, is a blind pocket. So how do you actually do that is a big question which you have to sort of program. So the methodology that so far has been covered has given you a very wonderful idea about how such a feature or a part can be recognized on the system. So we will probably try to take this problem up by first of all trying to mention all the surfaces which are there on this part. Let me just draw this surface again. So you have a feature of this sort which is there. Probably partially we are going to do this problem today and then maybe take it up in the next module. So this is another surface which is on, okay, and you basically extend the block in both the directions. You have a slot cut here, and I mention these surfaces to be starting from the surface across this blind pocket here, which talks about surface 1, 2, and then there is a surface 3, obviously a surface 4, okay, along these, and then you can also have the 5th surface somewhere here. There is a 6th surface, there is a 7th surface here, and there is also going to be a 8th surface underneath. So this surface underneath here is the 8th surface, and then there is a 9th surface on this particular side, a 10th surface here, a 11th surface here, a 12th surface here, and then obviously there is a 13th surface somewhere here, and then there is another surface at the back end here, which is the 15th surface. So the first thing that we do here is to make the graph here. So let's say we start with the graph 1. So you have 1 as a node, then you have 2, then you have the surface 3, surface 4, and they are all interconnected. So 1 and 2 are interconnected. For example, you have also the surface 5 somewhere. So let's just write it in a little more in a manner just close to what we did actually before. So we start with, let's say, these 4 pockets, 1, 2, 3, 4, and let's say there is a 5th pocket here. So we do all the interconnectivities between the different pockets and mention or give the attributes 0, 0, 0, 0, so on and so forth on this particular slot right over here. And then we also try to connect with these surfaces some of the other surfaces which are in existence. So obviously the 6th surface would be connected to all these surfaces by different means, where there are convexities. So to the first surface, for example, or the 2nd surface, for example, or even the 4th and the 3rd surface. So all are connected through convexities. And the 6th surface again is connected to the 7th surface through a convexity. The 7th surface is also connected to an 8th surface through another convexity. The 8th and 9th are again interconnected through another convexity. So on the 10th surface. So if we look at, let's say, the 9th and the 13th and the 10th surface. So you have 9, 13, and you have 9, 10. So these are both connected through convexities. 10 and 11 obviously would again be connected through a convexity, but between 11 and 12 you are having a concavity, and similarly between 12 and 13 you are having another concavity, and the 13th surface finally is also connected to the 15th surface with a convexity, and so on is the 10th surface. The 10th surface also is connected to the 15th surface with a convexity. Similarly, the 10th surface, the 13th surface is connected with the 15th surface also with a convexity. Okay. So then obviously the 13th is also connected to the 8th surface with a convexity, and the 13th also gets connected to the 6th surface with another convexity. Okay, because at the back end there is the 15th. Yeah, so the 13th surface has a convexity with 6th surface, and so has the 15th surface. So if you look at the 15th surface also, it has the connectivity to the 6th surface with the convexity. Okay, so in a nutshell, that is how all the surfaces are kind of defined. And there is also a 14th surface somewhere here where we have to connect the 14th to the 12th or 11th or 10th. So we make the 14th somewhere here. So let's connect that to the 11th with a convexity, 12th with a convexity, 10th with another convexity, something like this. And also the 14th is connected in a way to the 6th substrate with another convexity, and so it is connected to the 7th with another convexity, and the 14th is again connected to the 8th with another convexity. Okay. So, this is a very complex adjacency graph which has been developed, and from this graph in the next step, probably in the next module, we are going to find out what is that matrix representation which will lead us to actually figure out what are those areas where there are features on the particular subpart in question. So, with this we come to the end of this particular module. Thank you.